Hello, everyone. Thank you for joining our technical discussion group. Before we open the session, we're going to wait for a couple of minutes to allow our colleagues to dial in. So probably about 5 minutes. We're going to start even at 7. Yeah, 5 minutes to 7, Jakarta time. Thank you. Good morning, good afternoon, good day, ladies and gentlemen, wherever you are. A very warm welcome to you all, our honorable speaker, participants, students, and professionals. It is an honor to be here with you today, and our sincere gratitude for joining SPE Young Professionals Technical Discussion Group organized by SPEYP Java Indonesia section. I am Devatasya Olita. I'm a reservoir engineer working with Schlumberger Indonesia, and also I'm as the SPE Java YP chairperson. And today I will be your moderator for the discussion themed reservoir simulation for CO2 storage studies. As we know, the oil and gas industry has changed tremendously in the past years due to energy transition and digital transformation initiatives. This change will continue to take place in the coming years and will definitely affect the required experience and skill sets of the future engineers in the energy industry. Even now, a lot of companies have reshaped their portfolio and re-strategized their business model and future plans to adapt with the changes that we expect to see in the industry. In this session, we will discuss and learn about one of the promising technology that could play an important role in reducing CO2 emissions in the atmosphere, carbon capture, utilization, and storage, or CCUS for short. And to optimize the implementation of this technology, it is crucial to fully understand the behavior of our proposed reservoir. How much CO2 can be stored? What are the possible injection rates? What are the risks of leakage? In the session, we will discuss reservoir simulation features that Schlumberger provides in the software, along with the workflows for CO2 storage. Introducing our speaker, Mary Ann Giddins. Mary Ann is a Schlumberger advisor in reservoir engineering based in Abingdon Technology Center, UK, where she provides technical advice on reservoir simulation software, workflows, and integrated studies. Her areas of expertise include advanced reservoir engineering applications such as enhanced oil recovery, gridding, upscaling, uncertainty, and optimization. Mary Ann's experience ranges from simulating laboratory EOR experiments for a core 5 centimeter long to optimizing simulated performance for studies of the biggest oil fields in the Middle East. She's a mentor and coach for trainees and experienced engineers at all stages of professional development and has supervised over 80 student intern projects, which actually also include my own master's thesis project when I was an intern in Abingdon Technology Center. Okay, so before we continue to the speaker session, I would like to remind the participants, if you have any question, please type them in the chat box feature in the format name, dash by mic or by chat, that's the question. And the details of this information will be posted by the committee in the chat box. Now, without further ado, let's welcome our speaker, Mary Ann. Mary Ann, over to you.
Thank you, Deva. Can you hear me?
Yep. Mm-hmm.
Okay, I'm going to share my screen now. So you should be able to see the first slide in my presentation. Please let me know if that's okay.
Yeah, we can see it.
Okay, very good. So first of all, thank you so much for the invitation to speak and for the introduction today. I'm going to welcome you on a virtual visit to Abingdon Technology Centre in the UK. So first of all, let me introduce you to the Technology Centre. And you will see we're a centre of excellence in reservoir engineering for all of Schlumberger. We do software development there for reservoir engineering. We have expertise in multi-phase flow in porous media, dynamic reservoir and well modelling, gridding for reservoir simulation, fluids and PVT modelling, integrated asset modelling, geomechanics, high performance computing and cloud technologies, innovation projects including digital applications, and we also support our software usage internationally. We take part in studies, we give training, and we work on collaborative projects with clients, other Schlumberger segments, universities, and other third-party vendors. So we have a very busy time when the office is open, and there are usually about 200 people there. At the moment, it's empty, like in this picture. And I'll show you what my office is like at the moment. So for the past year, I've been working at home, surrounded by trees, flowers, birds, animals, and surprisingly, with a lot of communication with everyone, not only my colleagues who are also working at home, but everyone in the world. So a few years ago, I would have to travel to give this presentation, or you would have to travel to me. Today, we can have instant communication, even from such a long distance. Here's the agenda for my presentation today. So I'll start with some background information on CO2 storage. Then I'll talk about CO2 dynamic modelling, what's required and what we need to do. And then I'll describe more specifically some of the options we have available in our simulators for storage in saline aquifers, depleted gas reservoirs, and depleted oil reservoirs. I'll give a bit of information on some more extended modelling capabilities for other CO2 related behaviour. I'll talk about the integrated workflows which involve reservoir simulation but also other workflows, and a bit about the software solutions that we're gradually evolving and improving. I'll finish with some case studies and then some conclusions and discussion. So first of all, the background. Carbon dioxide. Carbon dioxide is regarded as a problem, but it's also essential for life. It's the source of food through photosynthesis in plants. It's exchanged between the atmosphere, the land and the oceans in a carbon cycle. So there has always been carbon dioxide in the atmosphere, and it plays an important part in influencing the climate. It's what they call a greenhouse gas, and these are atmospheric gases that absorb and emit infrared radiation. And they include not only CO2, but also water, methane, nitrous oxide, ozone, and some more complex molecules called halocarbons. CO2 may have the most significant effect because its peak absorption is very close to the peak atmospheric infrared wavelengths. So it's quite possible that CO2 working with the atmospheric wavelengths has the most significant influence on the climate. Just to confirm that greenhouse gases are not entirely bad, the average surface temperature today around the world is about 15 C. If we didn't have any global warming, the average temperature would be -18, which would mean that life would be very hard to sustain as we know it. In addition to the greenhouse gases, water vapour and clouds can contribute to warming, but there are also cooling effects, what they call aerosol effects, which can be caused by liquid or solid particles in the atmosphere. So in a balanced climate situation, carbon dioxide is an important thing of positive value, but as we're seeing, if you get too much of it, it can lead to trouble. How much CO2 is in the atmosphere? This is a question that many people ask. The table on the right shows you the percentages of gas and the volumes in dry air. So nitrogen is the most common gas. Oxygen is the second commonest gas. And then we have quite small percentages of argon, which is nearly 1%, CO2 is actually the fourth commonest gas, but it's only 0.04% approximately. There are also many traces of other sorts of gases, and the atmosphere does contain water in variable amounts, so probably on average about 1%. So this is one reason why people have not taken CO2 seriously in the past, because the total is quite small. But as I mentioned, the issue is with the greenhouse gas impact due to radiation. And also the amount of CO2 is increasing. So emissions from things like fuel burning, industrial processes, they're called anthropogenic emissions, and they're leading to an increase in the amount of CO2 in the atmosphere. So if we look to history, prehistoric ice cores can be analysed to estimate the atmospheric concentration of CO2 when they were exposed to the atmosphere, and they actually show up to 300 parts per million of CO2 in a variable amounts over history. Since 1750, when we entered what you might call the industrial age, the amount of CO2 in the atmosphere has increased from about 280 parts per million to 415. So this is way higher than we saw in history. This is shown on this plot on the right. Also, during that period of increase in CO2, the temperature has been increasing. And in fact, the average temperature has gone up by over 1°C since 1950. So this again is indirect evidence of the impact of CO2 increase. So most of the audience, I expect, will be reservoir or petroleum engineers, and we do like to understand the numbers that people are talking about. So I should mention the units. 1 part per million of carbon dioxide is equivalent to about just over 2 gigatons of carbon, or 7.8 gigatons of atmospheric carbon dioxide. And to convert it to gas volumes, 1 ton of CO2 is about 535 standard cubic meters. So this gives you some idea of what sort of numbers are involved. We also need to think about where are the global emissions coming from. So these analyses are from the BP statistical reviews and Energy Outlook from 2019. And I continue to use the 2019 figures because 2020 was such an abnormal year. So the CO2 emissions by sector can be divided into power, industry, buildings and transport. By far the biggest emissions in 2017 were from power, but there's also been increasing impact of industrial emissions and emissions due to transport. We can also look at where the emissions are coming from in the world. And clearly the nations who are developed and working in industrial economies are producing much bigger emissions than the rest of the world. However, as many of the developing countries start to increase their energy usage, the quality of life is improving, but also their CO2 emissions are increasing. So we need to allow for the possibility that CO2 emissions will continue to increase. The International Energy Agency has been analysing and making predictions on global emissions and the impact they will have on climate. And they produce reports from time to time about not only what emissions are happening, but how can the emissions be reduced. So one possibility for reducing emissions, in addition to improving efficiency and replacing energy with renewables, is to be able to capture and use or store the CO2 when it's produced. So, for example, a gas production process, a power station, some other industrial source can emit CO2. If you can capture it at the point where it's being emitted and then either use it for another process or store it, then we can be aiming to reduce the amount of CO2 in the climate. So utilisation can include other industrial processes, may also include enhanced oil recovery or enhanced gas recovery. Storage underground can be in saline aquifers or depleted hydrocarbon reservoirs. And although on the plot, the potential reduction due to CO2 is shown as being around 9%, this is still quite a significant effect. And it's really essential to have CCUS in process in order to meet the real hard targets that are being imposed for the future. Of course, it needs economic incentives or legislation for people to have a reason for using carbon capture and storage. Then we need to consider how much CO2 can actually be stored. What can we do? What's the capacity? And can we have an impact? So at the moment, there are a few individual projects going on around the world, capturing about, per project, capturing about 1 megaton per year. And the current global total is 35 megatons per year. The future scenarios, which are being considered by governments, propose capturing between 1 and 5 gigatons per year. So this is a really big increase. However, studies have shown that this should be feasible if we can make good use of the technology and skills of the oil and gas industry to find good storage sites and to perform the injection processes. So you may have seen in the news all sorts of recent initiatives and announcements. Countries are announcing net zero targets for emissions. Major oil companies are announcing sustainability targets. There's a lot of industry collaboration on CCUS. And just to give another idea about the size of these projects, here are some current projects. So in Abu Dhabi, CO2 is captured from the iron and steel industry, and that's at a rate of just under 1 megaton per year. In the US, in Decatur, they have an ethanol plant, and again, the capture rate from that plant is around 1 megaton per year. In Australia, CO2 is being captured from natural gas production at around 3 to 4 megatons per year. In Texas, in Petronova, there's a power generation plant, and again, capture rate is about 1.2 megatons per year. So at the moment, these projects are quite small because basically they're capturing CO2 from one specific source and then storing it. However, there are much more ambitious projects now being considered where, for example, you might have a large storage area and take inputs from many sources. Schlumberger has been working in this area for about 20 years now, specifically working on CO2 storage technologies, implementation of pilot studies and CO2 storage sites, providing services for site selection, appraisal, planning, construction and operation, performing multidisciplinary studies including geology, geochemistry, geomechanics, and dynamic flow modelling, looking at uncertainty and risk analysis, but also being involved in actual drilling, well construction, site operations, monitoring and verification. So we've been involved in over 50 major CO2 storage projects so far, including projects in Norway, Algeria, Australia, and the USA. The picture on the right is of CO2 injection facilities at a storage site called Sackrock in Texas, where They are piloting CO2 storage, but also using CO2 for enhanced oil recovery. The picture was taken in 2016 and shows the scale of this operation in Texas. Okay, so before I go on to the dynamic modelling presentation, quick check that you can all still hear and see.
Yes, Marianne, I can see it.
Okay, very good. So I don't want to keep talking to myself. Okay, so now I'll talk about the dynamic modelling requirements for CO2 studies. CO2 storage studies cover a whole project life cycle, which includes selection of the site, appraisal and characterisation of the subsurface, developing the plans to operate the storage, commissioning the storage, performing the CO2 injection over a period of time, then at the end of the injection to close, to check the status of the storage after closure of the injection wells, and then to be able to transfer to some authority or long-term custodian, because CO2 storage is not just limited in time to the time when you're performing the injection. You have to think what will be the fate of the CO2 over a long period of time, which may be hundreds or thousands of years. So this is what is different compared to oil production processes. There are lots of government regulations on CO2 storage, which give guidance on the studies that are needed. And the SPE also publishes some guidelines for CO2 storage resource management. So these regulations indicate that dynamic modelling and understanding is of vital importance. So I'm not going to read all the words in this table. It's taken from an EU directive from 2009, which is called the guidance document on characterisation of the storage complex, CO2 stream composition, monitoring and corrective measures. So essentially what they're requiring for anyone who is going to store CO2 in Europe is that they perform studies which include data collection, characterisation of the storage site and the complex in a 3D geological model, dynamic modelling to understand how the CO2 injection will perform, sensitivity studies to check whether any of the assumptions about the storage capabilities may be a problem, and then also risk assessment to look at the safety and the integrity of the site and see whether there are any risks of leakage or whether it's possible to keep the site safe over a long period of time. So these regulations require that people perform the necessary studies, and you can see that in all of these steps there's a demand for the technical capabilities of reservoir engineers and other oil industry experts. We also need simulation to decide how to monitor the CO2 storage sites through the life cycle. So monitoring a site using things like permanent observation wells or 4D seismic, in theory, is likely to work, but it's also very expensive. So someone who wants to store CO2 needs to decide what's a cost-effective way to maintain the integrity of the site and to monitor the site performance while meeting the regulatory requirements. By dynamic modelling, you can identify what are the key parameters, the uncertainty ranges, and predict behaviour over the lifetime of the storage, which enables you to design and plan measurements. After you've taken the measurements, you can also do history matching exercises to see whether your original assumptions were correct or whether anything is changing quite dramatically differently to what you predicted. And of course, you need to meet the requirements for long-term custodianship as well as short-term. So there may be measurements that you will take initially when you start the injection to find out what was the impact of pressure and temperature changes. Is the injection well operating as expected? And is the CO2 staying in the site where you predict it will move to? You may also need to plan much longer term measurements to confirm that the site is not leaking. And clearly with those, you need to think about what sort of time interval will you take the measurements. You know, do you want to have monitoring continuing for the next 1,000 years, or can you make recommendations about when some specific measurements should be taken? So all of these requirements are pointing towards the need to be able to perform reservoir simulation studies for CO2 storage. And it's going to help you to answer key questions like, what's the capacity? How much CO2 can you store? What's the injectivity? What injection rates are possible, both in terms of being able to get the CO2 into the porous media under the subsurface, and also how the wells should be operated? And containment. So again, working out what are the risks of leakage and what can you do if you have a problem. There are several storage scenarios to consider. Saline aquifers offer a very large volume. There are many depleted oil and gas reservoirs now in the world, which actually have a lot of infrastructure which might be reusable for CO2 storage, and where we also have some idea of things like the caprock and the characterization of the storage site. We also have the option of performing enhanced oil recovery or enhanced gas recovery and storing CO2 as a result of injection for those schemes, which may be an attractive way to start because it will possibly be more cost effective than going straight to a storage scheme. In order to study those, we need to be able to model this multi-phase complex physical and chemical behaviour, which is special to CO2. We also need to be able to simulate over long time scales. So again, hundreds or thousands of years, not just the life cycle injection period. In Schlumberger's simulators, we have various options that can be used for CO2 storage studies. So on the simplest level, many of the early studies of CO2 used CO2 as part of a black oil approximation, in which CO2 was represented as gas or solvent, or possibly even you had a two-phase model in which CO2 was gas, and you actually used the oil to represent a dummy water phase. And you can do that sort of study very simply in Eclipse or Intersect or FrontSim. But of course, it doesn't include anything that will really tell you about the long-term fate when it comes to things like mineral reactions over the longer period of time. So in order to handle the storage aspects of CO2 storage, as opposed to just the injectivity and volumes, we need special features, and these were developed originally in Eclipse Compositional or E300. So we have some keywords which are used to refer to these specialist options. CO2 store is for geological storage in aquifers. Gas watt is for depleted gas reservoirs or aquifers and enhanced gas recovery. CO2 sol is for depleted reservoirs and enhanced oil recovery. And of course, you can also study enhanced oil recovery today in the Intersect simulator. And we also need to be able to integrate our simulator with other tools for more detailed studies and workflows covering things like geomechanics, geochemistry, pipeline networks, etc. Sort of things we need to do in our CO2 simulation include having the reservoir parameters properly defined to cover characteristics like temperature, salinity, permeability, residual gas saturation. The dip of the reservoir can have a significant effect on the injection behaviour. The pressure of the reservoir may determine what phase behaviour you expect in CO2, particularly when you consider it alongside the temperature. And of course, you want to know about the heterogeneities of the reservoir, which also have a big impact on CO2 storage behaviour. Need to be able to model physical and chemical effects. So for CO2, we need a solubility model to show how it interacts with water. We need to consider the geochemistry. We need to look at hysteresis effects in order to understand the possible residual saturation that will be left by hysteresis. And we need an equation of state model for the phase behaviour. In designing the simulator, we also need to think about things like discretization and boundary conditions, where again, the boundaries that you use for a huge saline aquifer may be defined in a different way to the way that you would normally identify the area of interest for an oil reservoir. You need to think about the grid design because the cell size, it's important to have a fine enough grid to capture the CO2 behaviour, but you don't want it so fine that the simulator takes days and days to run. So we have the usual trade-offs with upscaling. You need to be able to model aquifers on the outside of the storage area. Look at the well models, and again, consider whether you need to model geomechanical behaviour in detail to make sure you retain the reservoir integrity. Then, of course, in our simulators, we also need to represent the operating strategy for well placement, injection, surface facility constraints, and to be able to model the level of detail we need to design a monitoring scheme. It's worth mentioning at this point the kind of trapping schemes that we need to model in a dynamic simulation. So there are four major effects which can lead to CO2 being trapped. First of all, when you first inject it, structural trapping is of great importance. CO2 will migrate from the injection site due to pressure and density gradients, but it may be trapped by cap rock or structural features. So this is something you want to look at very early in this study. If you're working in an aquifer zone, you need to be sure that there's some way to trap the CO2 in the aquifer, that it won't just migrate out again. Then we also have the impact from hysteresis of what they call residual trapping, in which the gas phase can be immobilized just due to gas trapping from relative permeability and capillary pressure effects. When the gas remains in contact with water, it will dissolve into the aqueous phase. So there you have the impact of solubility trapping. And finally, over the longer term, mineral trapping can occur because of interaction between the dissolved CO2 in the water and the reservoir rock. So the CO2 will be transformed into a mineral, in which case it's trapped permanently in the storage site. These are all things that we want to model with the simulator. Okay, so just pausing again to make sure I'm still online.
Yes, Marianne, we can hear it clearly.
Okay, very good. So now I'll talk a bit about the storage options in the simulators in a little bit more detail, which gives some more idea of the kind of things that we need to model. First of all, the CO2 store option in Eclipse. This was designed especially for our carbon services experts who were involved in CO2 storage projects. And they made a request for a fairly simple model that would handle almost all the phenomena that you see for injection in saline aquifers. but which it would be relatively easy for someone to set it up in the early stages when parameters are uncertain. So CO2 store will model the chemical reactivity, the phase behavior in systems containing carbon dioxide, water, and salt. It has three phases: the CO2 rich phase or gas-like phase, the H2O rich phase or water phase, but also a solid phase to represent the mineral reactions. It contains 5 major chemical components, which are CO2, water, salt, calcium chloride, and calcium carbonate. And it has accurate calculations for the solubility of CO2 in water and water in gas. You can have analytical aquifers, which have their own user-defined aqueous composition. And there's also available a thermal option for CO2 store, in which you can model temperature-dependent effects. The phase behavior in CO2 store is quite similar to the way that you model phase behavior for compositional typical oil reservoir studies, except that we need to consider the mutual solubilities of CO2 and H2O. And that's done by a fugacity method, which was published by authors such as Speicher. The water fugacity calculation is done using Henry's law, and the CO2 fugacity calculation is done using a modified equation of state. Several parameters affect the solubility. So solubility of CO2 in water increases with decreasing temperature and with increasing pressure. It decreases with increasing salinity. So some people might ask, why do you inject in a saline aquifer if it reduces the solubility of CO2? And the answer is because there's a very large volume of saline aquifers available for injection. And also we don't want to contaminate fresh water. So if the water is fresh enough for CO2 to dissolve really easily, then it's probably also fresh enough to be used for drinking water and agriculture. So we need to understand the interaction with salinity, not reject saline storage water. The calculations in CO2 store are tuned to match the experimental data for typical CO2 storage conditions. So that's between 12 and 250 C and pressures below 600 bar. Some of the effects that you see when you run a simulation model of CO2 include the gravity and buoyancy effects. So here we have a view of a CO2 hypothetical storage model after 500 years, after 1,000 years, and after 2,000 years, where you can see the CO2 is fingering down into the water. What happens is that, first of all, you have convective flow, which leads to CO2 initially having been injected as a hydrocarbon-like gas or single-phase fluid. It rises to the top of the aquifer. Then it starts to dissolve in the water. Brine containing dissolved CO2 becomes heavier, and then it drops down in the reservoir. So this picture is very pretty. Obviously, in real life, reservoirs are not flat, but this is the kind of study that you might want to do to determine the long-term fate of the CO2. I'll also mention the chemical reactions that we use to handle the interactions with brine and solids. So brine density is corrected for dissolved salt. And we have the chemical reactions to represent salting out, in which perhaps the water evaporates into the CO2 and you're left with a lot of salt near the injection well. And also to consider equilibrium chemical reactions for generation of calcium carbonate over time. We can include user-defined mobility multipliers to define the effect of the adsorbed solids, and we can also calculate the acidity or alkalinity of the water based on the active coefficient and the presence of the H+ ion in the aqueous phase. I just mentioned salting out. This is an interesting phenomenon that can occur in very saline water. So if you inject CO2 into water at a high rate, the water in the brine can evaporate into the gas, and it results in a dry out effect near the injection well. You can even get to the stage where the residual water saturation is reduced to 0 because all of the water is taken away by the injected gas. And of course, this may increase the effective permeability and improve the injectivity. However, if you have high salinity brine, you also have this risk of salting out because as the water evaporates, the salinity increases. You then get halite precipitation, causing scaling, permeability and porosity reduce, and that can reduce the injectivity. So this kind of phenomenon needs to be considered when you're thinking about completion design and injection operations. Now I'll talk about CO2 storage in depleted gas reservoirs. So we have a special option for depleted gas reservoirs called gas watt. This uses a different formulation compared to CO2 store. It's been designed for gas storage in depleted gas reservoirs or aquifers, or possibly for enhanced gas recovery. Here we consider just two phases, the gas and the aqueous phase. We have any number of hydrocarbon components plus CO2, nitrogen, H2S and water. And any of the gas components can be soluble in the aqueous phase. So this is handled by an equation of state model for the phase equilibrium. It contains gas-water relative permeabilities. You can consider molecular diffusion of the components and also use aquifers attached to the reservoir. You can also consider the gas quality and the calorific values. So if you were injecting CO2 in order to produce natural gas, you want to know whether you're really producing methane or whether you've actually got so much CO2 breaking through that you can't meet contract values. The gas watt equation of state is a modified Peng-Robinson model which was published in 1992. You can construct the parameters for this model by matching observed lab or field data. It predicts the liquid mole fraction of CO2 very accurately. The amount of water in the gas phase may not be quite so accurate as for the CO2 store option. Generally, the calculations being done here are isothermal, but you can say that the reservoir temperature is defined for every grid cell, or you can have temperature dependent, depth dependent temperature model. So the salinity model is a little bit simpler also in gas watt, so it doesn't actually model the salting out effects that are available in CO2 store. Then the third option I'll describe is CO2 storage in depleted oil reservoirs. So for this we have the CO2 sol option. It can be used for enhanced oil recovery as well as for CO2 storage studies. So you can use it when you're working with miscible or immiscible gas injection or for WAG processors for enhanced oil recovery. You can handle three phases here, so oil, gas and an aqueous phase, where CO2 can be present in all of those phases. In this case, water is not vaporized in oil or gas, but we do use calculations of CO2 solubility in water, depending on pressure, salinity, temperature and composition. We have some other related options for hydrogen sulfide and for general gas solubility in the aqueous phase. They're all tailored for specific types of studies. Some of the features of CO2, it assumes instantaneous equilibrium between the oil, gas and water phases, and you can model CO2 solubility by a fugacity function. It has an optional water relative permeability model where you can look at the impact of having mixed components in the water, and you can model molecular diffusion between gases. Just to give an idea of the impact of salinity on CO2 solubility, here the top picture shows an experiment where fresh water is used, and there's very high solubility of CO2. So the red shows the CO2 breaking through towards the producer. It's a fairly small amount compared to what happens if you use seawater with higher salinity. CO2 is not so soluble, so here you've actually got much more gas travelling towards the producer compared to what happens with fresh water. It's also worth mentioning what's involved in designing CO2 EOR processes and the kind of studies that need to be done. Similar studies are also required for CO2 storage. So I've already mentioned that CO2 behaviour is complex. It can form two liquid phases. In practice, it's unlikely that CO2 injection will always be miscible, but you can still achieve some enhanced oil recovery even when you're below miscibility pressure. And again, we need to understand the physics of the gravity and buoyancy effects, the impact of heterogeneity, interaction with water, and in the case of enhanced oil recovery, if there's a lot of oil in the reservoir, you may also have risks of asphaltene precipitation. Here's a diagram showing modelling of different CO2 WAG processes. So the top three lines show different cases for a homogeneous reservoir. Bottom three lines show different cases for a channel reservoir. And they're all using similar CO2 injection schemes, but in some cases we have water alternating gas. And in some cases, although we're still doing water alternating gas, CO2 is being injected at the bottom of the reservoir and water is being injected at the top. So you can see the different impacts and the different rates at which you might get breakthrough at the producer. So CO2 EOR studies are fascinating in themselves. Now I'll talk about some of the extended modelling capabilities. So I mentioned that we have a CO2 store thermal option. So you can use this to understand the impact of temperature. It also allows you to have an oil phase plus a gas phase and a water phase, and to simulate the thermal properties of rock. This is quite a general option. It's also applicable for geothermal simulations, and we have validated it against the Stanford geothermal program comparison examples. If we want to go beyond the basic capabilities available in all those options, we can also use user-defined chemical reactions to make a more generalized model, possibly as an alternative to the CO2 sol option for complex cases. And here you would define explicitly what the composition of the brine is by using a multi-component water description. And you can tune the reactions to match the measured data, or maybe to match CO2 store results for solubility in the aqueous phase. And then you can define chemical reactions to represent mineral dissolution and precipitation. This kind of method is also applicable for other studies like low salinity water, souring and scaling. So this gives you a way to generalize the underlying model. Although it may be quite a hard job to build such a model, you might want to start with a simplified model to understand how sensitive things might be to chemical reactions before you build a very complex case. So now I'm just checking the time. According to the schedule, I should talk for an hour, which gives me 5 minutes. But I think there's plenty of time for discussion, so maybe it's okay if I slip slightly over that deadline.
Yep, it's fine, Marianne.
Okay, good. So I'll mention some of the integrated workflows that go into a CO2 storage study. So we need to think about the whole supply chain, what's actually going into the storage unit, and we need to think about upstream activities as well. That can include what happens at the source when CO2 is captured and separated, how it's transported and compressed, and how it's injected into the reservoir. So interestingly, in the North Sea, there are lots of studies going on about transporting CO2 by ship to offshore installations for injection. And there we have the interesting consideration that when you transport the CO2 by ship, you don't have a continuous supply. You may have interruptions in the injection while one ship is going off and another one is coming in. So we need to be able to model what happens when you have an intermittent injection process. We also have to put a lot of emphasis on uncertainty, because if you're working with a saline aquifer, you may have very limited subsurface characterization data compared to what you normally know about an oil field after a period of operations. In order to study this, we use Petrel as the platform for performing multiple realizations. We can also use MEPO, and we need to consider what are the significant uncertainties and how can we test the impact of those uncertainties. So the pictures on the right show probability maps looking at the probability of 5% CO2 saturation after a period of time. So the top map shows cross-section with the probability of greater than 5% CO2 saturation after 3 years of injection. The bottom map shows an aerial view looking at the probability of 5% CO2 saturation after 50 years. How far is it going to travel in the reservoir? And those plots were actually originally set up for someone who was doing a 4D seismic analysis to see when would be a good time to take seismic measurements to identify the plume position. We also need to think about geomechanics. So it's quite possible that even if you're injecting in a former gas reservoir, a caprock seal that works for natural gas may not be a seal for CO2. There's a risk that if you inject CO2 at a high rate and therefore at a high pressure, it may lead to fault reactivation or possibly caprock failure. So you need to design the injection well to maintain a safe injection rate while still achieving rapid enough injection. And of course, geomechanics also provides you with the rock physics analysis you need in order to perform any time-lapse seismic studies. So again, in the North Sea, they're starting to look at the possibility of using horizontal wells for injection in order to maximize the injection rate, but possibly at a lower pressure. In the past, people generally considered only vertical wells for CO2 because they were doing relatively low-cost pilots. But if you had a large enough volume of CO2, then possibly the well design is going to be an important decision, depending also on the geomechanical behaviour. And we can use integrated modelling to bring together all of the different tools for performing a study, which includes the surface facilities, the pipeline facilities, possibly multiple reservoirs coupled together. So you might have one reservoir which is producing CO2 and you want to pipe the carbon dioxide to another reservoir for storage. We're also starting to evolve new and updated software solutions as the demand for CO2 studies increases. So first of all, I think everyone has now heard of the Intersect simulator and knows that it's very powerful for compositional simulation and for advanced gridding for complex structures, fine detail, for heterogeneous models, and it's already able to model miscible CO2 injection, WAG floods, the effects of CO2 solubility in the aqueous phase. So it has a lot of the building blocks for modelling CO2. In the last year, we've had a lot of development activity to introduce chemical reactions in Intersect, including a solid phase. And we're also looking at more advanced fluid modelling, which will enable you to do specialist CO2 studies. So this is something that is clearly very important now, and we want to work to get Intersect qualified to meet the regulatory standards for being used for dynamic CO2 studies. We also have the option for possible extensibility by being able to call a third-party geochemical simulator. So the chemical reactions in our simulators will give you a nice high-level view, which you might regard as being upscaled chemical reactions. If someone has been doing a lot of detailed study of geochemical behaviour, then they may want to have the geochemical simulator working with Intersect. We're also doing a lot of work on multiple realisation workflows to improve the whole environment for performing multiple realisation studies, whether it's on-prem or in the cloud. And as I've already mentioned, uncertainty is very important for CO2. The governments and other bodies overseeing CO2 storage want to know that people have assessed uncertainty and risk as part of their analysis before they start to operate CO2 storage schemes. Now let's look at Delphi just briefly. Again, I think most people who have had any presentation from Schlumberger have heard of Delphi and the fact that it can enable on-demand reservoir simulation. So again, if you want to do a study involving a lot of simulation for carbon dioxide storage, then the option of being able to expand onto the cloud and to be able to do multiple simulations at the same time can be very helpful. So we're also considering how we can support CO2 studies effectively in the cloud. Finally, trying not to go too far over time, but I'll mention a few case studies which go back into the history of CO2 storage. So we have several examples of CO2 projects where Schlumberger has worked in North America. And we've been involved in projects that include seismic acquisitions, time-lapse logging, static and dynamic modelling for risk analysis, well design, drilling and completion, operations management and monitoring. These have included CO2 storage in saline aquifers and also enhanced oil recovery and storage. So we've been involved in some very large CO2 injection projects in the US, but also in some very long-running pilots where people have been gaining experience on what actually happens over the longer term. In the North Sea, the Sleipner Reservoir is one of the first commercial CO2 capture and storage projects. It was started 25 years ago now, and it's been operated by Equinor and partners. Their annual injection rate has been about 1 million tonnes of CO2 per year, and they also provided an early demonstration of how 4D seismic can be used to see where the plume goes. So this time-lapse seismic is actually from 20 years ago, and you can see that in 1994, before injection started, there was nothing much that you could see on the seismic plot. By 1999, after 3 years, you could identify where the CO2 plume was. And then by 2001, the CO2 plume was getting bigger, and you could see more clearly. You got a stronger signal because there was more CO2 in the reservoir. So this has been an early success, which is actually leading the way for other CO2 storage. And Schlumberger has been very much involved in the Sleipner project at various stages. Another early pilot, which got some useful data, not only for understanding CO2, but for understanding simulation, was the Ketzin pilot in North Germany, where CO2 was injected from 2008 to 2013. And since then, they've been monitoring what happened after the injection. So Schlumberger participated in the CO2 Sync consortium, which operated this pilot. We took part in modelling, risk analysis, operations and monitoring. And we were able to perform some very interesting simulation studies to predict the CO2 arrival time at observation wells and match that using history matching. So we tested out both black oil and CO2 store and streamlined simulation models and compared the results with some of the specialist academic software. Mufti is a modelling project that was done in European universities, and Tough2 is from the US. So they're regarded as being industry standard simple simulators, where we were able to demonstrate that we could match their performance. Well, actually, we could match their results. The performance was much better with our simulators. Another project where Schlumberger was involved, and again, this is over 10 years ago, which shows the amount of experience we've gained. This was for CO2 storage in a depleted gas reservoir in Australia, in which CO2-rich gas was being pumped, compressed, and injected into the Naylor field. And we performed a reservoir simulation study for that using the gas watt option, where we were able to match the dynamic behaviour based on monitoring measurements, predict the CO2 plume migration and dissolution, and identify what were the influential parameters for that storage. So these are just a small list. They are quite old projects because current projects mostly are under operation and may not be cleared for publication yet. But I think in the near future, everyone is going to be increasing their experience significantly on CO2 studies, even if not on CO2 implementation. Okay, so now I'll just make a quick summary and then we can go to the discussion. So just to summarise, in Schlumberger we have experience in all aspects of CO2 storage as a result of participating in industry-leading projects. What we know from our experience is that simulation is a key tool for understanding CO2. It's very complex. We have specialist CO2 options available now, and we're starting to implement the next generation solutions to make use of the performance of the simulator and the cloud technologies. The other thing that's clear is that multidisciplinary collaborative studies are essential, but also reservoir engineering is really the key to being able to design and manage a CO2 storage project. So we need integrated workflows and digital solutions to support the CO2 initiatives at every stage. So thank you very much. Shall I continue to share my slides while we start the discussion?
Yeah, sure. Probably some of the questions can be answered by the slides also, Marianne.
Okay.
Okay. All right. Thank you, Marianne, for the great presentation. I hope everyone in the room enjoyed it as much as I did. And now I will open the floor for some questions submitted during the presentation. I have a question here from Nisha. There are example of CCS projects, existing CCS projects, and how long have they been stored or injected, and how's the result after several years? This is probably regarding the monitoring, I think.
Okay, so as I mentioned, some pilot projects have been injecting for maybe 5 years to then see what happens next. The general assumption is that if you start a large-scale storage project and the capacity is enough, that injection could continue for up to 50 years. We've done some studies to find out where the plume might travel to. So generally, it's quite possible that even after injection, the CO2 plume will continue to move in the reservoir. We expect, as shown in this picture here, that CO2 will generally start to dissolve in water and to drop downwards in the reservoir. What we believe, again, from simulation studies rather from actual experience, of course, is that the plume will probably become stationary and you don't expect much movement after about 100 or 150 years. It will still exist as an independent molecule for a period of time, but gradually it will become mineralized. So, of course, no one knows exactly what will happen in 1,000 years' time. But you would expect that if you injected for 50 years and went back in 1,000 years' time, what you would find in the reservoir would be rock rather than gas.
Yeah. All right. Thank you for the answer, Marianne. We have another question here from Carrie. How well developed are the government regulations for CCS in countries outside of US, for example, in the UK or Europe, and how strict are they? Obviously, the environmental benefits are high, so perhaps the regulations are more relaxed than, say, fracking for oil?
So I would say the regulations are quite rigorous. I haven't mentioned any of the risks involved with CO2, but the reason why we need those regulations, first of all, if people are going to perform CO2 storage, we need to know that it's actually happening. So if you go to the government and report that you injected so many tons of CO2, they want to be sure that it's going to stay underground and not come back to the surface. And that may be necessary in order to get, for example, subsidies for the operations to make sure that you really have integrity of the site. Second point is that there can be some dangers if CO2 leaks. Some very rare occasions. There was an example where CO2 erupted as a result of volcanic activity from a lake in Tanzania. And actually there was enough CO2 low near the ground to suffocate animals or even people if they were there. Now that was a very rare event, but it's made people nervous. So they want to know not just that you're keeping the CO2 for the purpose of mitigating climate change, but that you're not going to have a leak that might cause any danger. So again, the risk may be very small, but you really need to be able to show that you've done all the studies to avoid that risk and that you're taking appropriate monitoring measures.
Mm-hmm. Yep. Does that answer your question, Carrie? If you want to ask directly, you can unmute yourself.
Okay, we can go to the next question.
All right, we have another question here from Heather. What are the leading methods of injecting to reservoir? Does Schlumberger have preferred or proven technology?
So we have experience of injecting CO2 in the reservoir. As I mentioned, generally people have been using fairly simple vertical wells, but we are looking at design of horizontal injection wells in order to increase the volume going into the reservoir without too much increase in pressure. The kind of things we need to look at are actually the geomechanical effects and the integrity of the well itself. So we need to make sure that we're not going to corrode the wells. So we may need to replace existing wells if we're going into a depleted oil or gas reservoir. So our flow assurance team and our completions team are starting to work together to make recommendations on the well design.
Okay, thank you, Marianne. We have another question here from Imade Agusiasa. Based on your experience in performing CO2 storage studies, what are the main uncertainty parameters which mostly impacting the success of CO2 injection?
So there are various significant parameters for CO2 injection. They include the basic things like the temperature, the geological structure, the pressure, and the salinity of the brine. Also, the effect of relative permeability hysteresis and other sort of minerals other than pure salt and calcium in the rock may also impact the CO2 storage. But I would say things like salinity and reservoir structure are the things that have a big impact on the early stages of the project.
Okay. I hope that answers your question, Mas Made Agusiasa. We have another question by Ivan Kurnia. So the question is, for CO2 EOR storage context, given a condition where carbon tax or incentive is available, could there be scenarios where oil production is sacrificed to allow more volume of stored CO2?
So every case is different and it would probably require some economic studies. However, given that we're now having targets being set for CO2 storage, there may be cases where you've reached the point where the oil recovery would be relatively low. But if you use the infrastructure of that oil field to inject CO2, you actually save a lot of cost of starting up the CO2 project. So it may be that some recovery may be sacrificed in order to have effective CO2 storage. At the moment, I would say most oil companies are still looking to optimize recovery from their assets as well as planning for CO2 injection. But if you reach the stage where the regulations on production demanded that you had to have a CO2 storage capacity and the optimum place for injecting it is in a depleted reservoir, you might reach the point where you say, well, you know, that there's no point in continuing to recover from that field because we need the storage.
Yeah. All right. Noted. There's another question here from Carrie. I've unmuted you, so you can answer. You can ask the question directly.
Thanks. Sorry, earlier I wasn't able to unmute. Thank you for an excellent presentation. My second question was, in carbonate rock aquifers, is there a big risk of dissolution of the carbonates if we're pumping CO2 into the pore space? And is this modeled in the Eclipse or Intersect CO2 store simulation?
Yes, so it's true. You might find that you do get some dissolution in carbonate rock. In the studies that we've done for specific reservoirs, so far what we found is that the interaction with the rock is at a relatively low rate compared with the time period of the injection. So it might be something that will happen over time. Clearly, if there was a lot of dissolution, it could lead to problems because you might have, you know, some kind of geomechanical effects if a lot of the rock dissolves away. But I would say most of the time dissolution of the rock is going to be part of the mineralization process rather than something that is an immediate problem, compared to the salting out case, where salting out is something that happens early in the injection stage. But it certainly needs study, depending on the, the geochemistry of the reservoir where you're working.
Okay, thank you very much.
All right, we have another question here from Rizky Harjadinata. You mentioned earlier that CO2 brine density becomes denser as CO2 dissolves in the brine. Does this phenomena apply the same way in CO2 oil density, as well as we know that CO2 will swallow the oil?
Yes, so certainly any molecules which are less dense than CO2, CO2 is quite a heavy molecule because it has oxygen in it instead of just hydrogen. So it can have density effects on any other fluid that it's dissolved or mixed with. And actually that's something else which means that you really need to have a fine scale reservoir simulator to capture the behavior of gravity as well as the other effects, and how that is also influenced by the heterogeneity of the rock. So, do you have is there a greater chance that the CO2 will drop to the bottom of the reservoir in a heterogeneous reservoir or a homogeneous reservoir? How well is the CO2 mixed with the other fluid? Or will you actually find that you don't get complete miscibility? And those sort of things are what you need to test with a dynamic simulation.
Yeah. All right. Hope that answers your question, Mas Rizky. We have another question here from Mas Pongga Wardaya. How long should be the monitoring done post last injection, for example, for the seismic? And the second question is, CO2 injection may change the permeability of the reservoir. It changes as the function of CO2 saturation. Is the reservoir model always updated, and how is it accommodated in the simulation?
Okay, so can you go back to the first question again? Sorry.
Sorry. Okay, so the first question is, how long should the monitoring be done post injection?
Okay, so that's something that we need to study again with dynamic simulation to estimate how long the monitoring should be done. Clearly, 4D seismic is expensive. You may not want to do full 4D seismic surveys too often. So perhaps we can use the dynamic simulation to work out when there might be a change in position that will be visible on a 4D seismic survey. Maybe we only need to do 1 or 2 such surveys. Maybe we need to recommend that another one will be done in the longer term future after the injection is finished. I would imagine that when people are operating very large CO2 storage areas, it may just not make any sense to plan to do complete seismic surveys over a large area too often. Maybe the operator will choose a pilot area where they will do some sample surveys and use that information to check what's happening and then decide whether to do a bigger survey. So that was the first question. Second question was about permeability changes in the reservoir with CO2 injection. Yes, so we can look at permeability changes as a result of CO2 interaction with the rock. And we can also look at relative permeability changes as a result of the fluid behaviour and model those things. If there's a major change in the reservoir resulting from significant dissolution, then we might also need to look at the geomechanical effects and how they influence the reservoir permeability as well.
Yeah. Okay. I hope that answers your question, Mas Pongga. We have another question here from Christian. What are the standard parameters in modeling induced seismicity in CCUS? And the second question is, which is the primary risk assessment in CCUS? Is it geological, economical, or environmental?
Okay, so for induced seismicity, we have this microseismic concept, and it's almost a whole presentation to go into how the microseismic is done. So maybe we need to skip it in this presentation. But we've probably got some papers explaining about how microseismic studies are done for typical unconventionals and other things. And we use similar methodology for microseismic for CO2. Second question.
Yeah. Second question is about the risk assessment in
Okay,
CCUS
risk
project.
assessment. Yes, so I think in the early stages of studying CO2 storage, people were very interested in the economics. But really, the risk assessment that's demanded by the regulators is much more concerned with the the physical risks of leakage and to make sure that containment will be achieved. On the other hand, if you're an oil industry operator, you may be looking at trade-offs between the opportunities for CO2 storage, possibly other new energy initiatives, and clearly economics is going to play a big part in whether or not CO2 storage is successful as a global solution to help with the climate change mitigation. So I'd say probably the physical risks are of critical importance, but we shouldn't underestimate the fact that we need to do economic studies as well.
Yeah. Okay. Thank you for the answer, Marianne. We have a lot of questions, but this is one of the last question here from Rika Vartita. So based on Schlumberger experience for the storage options, do we need to inject using new well or just use existing wells? And what are the key parameters in the simulation to ensure that the government has been that the government will approve of the project? Yeah.
Okay, so for the wells, if you have an existing depleted field where you already have wells that will meet the criteria for CO2 injection, or even for being used for observation wells, that's obviously going to reduce the cost of the project significantly. However, we need to think about whether there's likely to be any corrosion, both what's the condition of the existing well as a result of operations performed so far, and also is there a risk that maybe the metal that's been used in the completions will be corroded through CO2 operations and through the acidity of the water. So it's really something that has to be assessed again for individual fields. The comparison between the cost of building a new well, working over an existing well, or simply using an existing well with minimal alterations. Typically, when people are looking at CO2 completions, they need to be either very high quality steel or fiberglass. And we also need to think about the cementation around the well. So CO2 acidified water from CO2 operations can actually destroy some of the cements that are used in wells. And we have some special cement called Evercrete, which is actually designed to minimize the risk of being destroyed by CO2. So that might be something else that has to be considered. But I'm sure a lot of oil companies will be looking at the possibility of using existing wells because it's cost effective.
Yeah, agree. All right.
Second part of the question.
What are the key parameters that we need to consider in the simulation so that we can propose it to the government and the government will approve the project? I think that's what she means in the question here. Yeah.
Okay, so that's obviously part of the uncertainty analysis, and actually some of the studies early will be to identify what the key parameters are. you can actually read some of the European regulations and some of the SPE recommendations. The documents are published online. So there'll be some parameters that are requested for specific purposes, but they'll also want to see that the operator has considered what those parameters are and whether they identify any other risks as a result of their studies.
Yeah. Okay. Thank you, Marianne, for the answer. Mbak Rika, hope that answers your question. So that was the last question for the session. Thank you very much for everyone who has submitted the questions. And here in the comments in the chat box, I can see Pak Andi Bahtiar mentioned that he's glad that Pertamina is now working together with Schlumberger and Sukawati project. So Marianne, yeah, currently Schlumberger Indonesia is working with Pertamina in Sukawati project. Yeah. All right. This brings us to the end of the event. Thank you again, Marianne, for making the time for this event and the presentation and also the discussion. And thank you also for the participants for joining in. I hope that you enjoyed and learned a lot from our speaker's presentation and our discussion. Okay, so this is the end. Please stay safe and healthy, everyone.